Hello, everybody, and welcome to this micro lecture. And today we are going to discuss Poisson distribution, which is actually one of my favorite distributions. So I'm really looking forward to tell you about it. Okay, so what are the examples? First of all, examples. Without knowing it, you saw Poisson distribution many times. For example, if you have some service for an equipment and you need to attend the equipment that is broken, so the clients call and ask a mechanic to come, then a number of calls in a day or in a month will be approximately Poisson distributed. Another example that we see every day is a highway. So if it is a sunny day and no jam and the cars can freely overtake each other, then on a highway, the cars will also have Poisson distribution. For example, if you look at the number of cars on 1 kilometer of highway, it will have approximately Poisson distribution. So usually we say distribution models some real-life situation. So if you have to summarize what does the Poisson distribution model, then it's actually quite simple. The Poisson distribution models two situations. First is the number of random events in a given time, such as number of service requests in a month or in a day. And another, so there are more examples of this. For example, splitting of an atom in 1 second, the number of splittings of an atom also has a Poisson distribution. And for example, if you have a web shop, then number of purchases or a number of visits to a web shop in an hour also will have Poisson distribution. So this is one, number of events in a given time. And the second one is the number of objects which are randomly scattered in a space. And space can be one-dimensional, such as a line, a timeline, for example, also, but also two-dimensional, such as some surface, or three-dimensional. Examples, for example, number of stars in 1 cubic light year of galaxy will be approximately Poisson distributed. And also, if a programmer writes a code, then of course we are humans, so we make mistakes, and there are usually errors in codes. And the number of errors in, for example, 1,000 lines of code will also have Poisson distribution. Okay, so now this is a real-life situation where it appears. But what is the mathematical model? So let's look at that. So first of all, we always have to introduce random variables. So Poisson random variable, if we denoted by capital X, will usually represent a number of random events in time or a random number of randomly scattered objects in space. And the probability distribution will look like this. This is a little bit a scary formula, but we will see later on where it comes from. So the probability that this random variable takes a particular value x, small x, is defined by this formula on the right. So there is an exponent involved, and mu to the power x and x factorial. And you already see that there is a parameter mu. Well, of course, x as a random number of events or random number of objects, it can be 0, 1, 2, 3, etc. But what about mu? Well, mu is always positive, and in fact, mu is nothing else but expectation of x. So if we have a random number of events in a given time period, then mu will be average number of such events. And if we have a random number of objects scattered in a space, in a certain part of space, then mu will be average number of such objects. So let's look at now at the distribution. How does it look like? So yeah, by the way, the variance also will be equal to mu. And here is how distribution looks. Okay, so let's look at this plot a little bit. So what does it mean? Again, I can tell you that probability distribution is what? Distribution is actually is how we distribute probability mass among the points on the real line. So here, the points on the real line are non-negative integers, 0, 1, 2, 3, etc. And each integer receives a probability mass according to that formula, that probability that capital X is equal to that number. So now if you look at the distribution, so in this particular example, mu is equal to 5. And you already see that as x is 5 and x is 6 has the highest bars, and the height of the bar is equal to the probability of that particular value. So you see that 5 and 6 have the highest probability, and you can actually check that these probabilities are indeed the same. So it is most likely to observe average number of such events. Well, now values 4, 7 are also still quite likely, and then further you're from average, less likely is to observe that number. And indeed, if you have on average in a sunny Sunday, say 10 cars on a highway per kilometer on average, then it is very unlikely to see only one, or it's very unlikely to see 30. So this is how the Poisson distribution looks like. And now I promise that we will discuss where this formula comes from, and this is what we are going to do now. So Poisson distribution has another name, and that can be called a law of rare events, and that's exactly what explains the formula. So let's look how it works. So we consider that X, the Poisson distribution with U, that models the situations, and here is one example. Assume that we have this first situation, the number of random events in a given time. So we have one day, and we have the we're providing service for clients that bought some equipment, and the probability that a particular client will call on particular day is quite low. It is like 0.002, so it's 0.2%. Okay. However, we have 1,000 clients. So 1,000 clients, each of them has very low probability to call. Okay. So now we can be interested in different probabilities. For example, we have 3 mechanics. And what is then the probability that we'll have exactly 3 calls on that day? So exactly each mechanic will have exactly one job to do. So let's try to see how we can compute this probability. Well, first of all, we start with a model. So to start the mathematical solution, we have to start with a model. So we say, okay, let y will be the number of requests on this day. We denote it by y. So that will be number of requests, so it will be 0, 1, 2, 3, etc. Okay, then my question to you is, what distribution y has? Think about it, we have 1,000 clients, all are independent, each of them can call with probability 0.002, and we are interested in the number of calls. So what distribution will it be? If you think about it, then you realize that it will be, I will give you the answer now, think first yourself. The answer is it will be, of course, binomial distribution, 1,000. So it's binomial with parameters 1,000 and 0.002. Okay, so then what is the probability that x is equal to 3? Well, you already know binomial distribution. You can write it for yourself. I'm now giving you an answer. So this is the answer, and I intentionally put different parts of formulas in different colors. So the first component is 1,000 choose 3. A second component is probability of a call, 2 divided by 1,000 to the power 3. And the last one is opposite probability to the power 997. All right. So these are quite big, complicated numbers. So let's write it out a little bit. Again, the same colors. So the 1,000 choose 3, you can write it in that form. 1,000 times 999 times 998 divided by 3 factorial. We already see factorial showing up. Then 2 to the power 3 and divided by 1,000 to the power 3. And multiplied by this probability. Notice that what happens here. So now look, what if we want to approximate this formula, what can happen? So you can notice that 1,000 to the power 3 and this product 1,000 times 999 and 998, they're almost equal. In fact, if it was not 1,000 but 10,000, it would be even closer to each other. So more or less approximately they will cancel. Okay, and then what we will have left is 2 to the power 3 and 3 factorial. And what about this last term? So you see in this last term, 1 minus 2 over 1,000, this what is in the brackets is very close to 1. But it is slightly less than 1, but it is taken to the very high power also. So if you remember calculus, then you will realize that actually approximately you will have this expression 2 to the power 3 and 3 factorial will remain. And this last bracket, if you take a limit, if instead of 1,000 you take like 10,000 and then 100,000 and then 1 million, if you take this number going to infinity, then this bracket to this power will converge to the exponent e to the power minus 2. That is for the that just follows from the calculus. And now you already recognize exactly the Poisson formula. So 2 is nothing else but average number of calls. We have 1,000 clients and 2 to over 1,000 probability of a call. So on average, there will be 2 calls per day. And the probability that the number of calls will be exactly 3 will be exactly the Poisson probability. You recognize 3 factorial, 2 to the power 3, and e to the power minus 2. So that's how Poisson distribution arises. So now let's look at it a little bit in more mathematical terms, in more general terms. So if we have a binomial distribution where n is very large and the probability is small, so we define probability as just mu over n, we'll come back to it. So if we have a binomial distribution, then the probability that it is exactly, that its value is exactly x, converges in the limit as n goes to infinity exactly to the Poisson distribution. And that is exactly what was discovered by the French mathematician Simeon Denis Poisson very long ago. So let us look at it again. So it is a law of rare events. So what happens here? Remember that this formula is applied when n is very large, but the probability of success is very small. So when we take probability of success p equal to mu divided by n, then what happens when n goes to infinity? This will be a small number. So, and that is exactly the situation. N is large, p is small. And then approximately binomial distribution becomes a Poisson distribution. Okay, now we are going to look at another example, which again demonstrates how to use Poisson distribution as a law of rare events, as approximation of binomial. So this is a real life example that one of the students gave me. In the Netherlands, it is, of course, very important to have good train connection because the whole country is connected by trains. So there are big companies that are responsible for proper operation of trains. And one of them is ProRail, which is responsible for the technical side of it. In particular, they're responsible for this signs along the railway, the signs for the trains, where they can stop and when they can continue. Okay, so these lamps, of course, must be in order. They must be well operating. And within 1 year, with probability 2.5%, one light bulb can become defective. So what they do, there is a mechanic from ProRail, from this company, and daily this mechanic checks 120 signs, so altogether 360 lamps. And whenever the lamp is defective, it gets replaced. But this mechanic carries 15 lamps. So the question is, what is the probability that the mechanic will run short of lamps? There will be no lamps, not enough lamps to replace everything. Okay, so how do we solve this? Again, we introduce a random variable, a number of defective lamps, and then what is the distribution of this random variable? Well, we have 360 lamps, and with probability 0.025, each of them can be defective. So it's binomial distribution, again, with parameters 360 and 0.025. Okay, so now that is a typical situation for Poisson approximation, large n, small p. So what we can do, we can approximate binomial distribution with Poisson distribution. So what will be the mu? Well, remember from the limiting result, mu has to be p divided by n. So, p is mu divided by n. So mu is n times p. Indeed, mu is an average. So we have 360 signs right? And the fraction of defective is 0.025. So you have to take the product of the two, and you get 9 defective lumps on average. So you already see that carrying 15 lumps should be quite good, right? So we should not run out of the lumps very often. Okay, so 9 defective lumps on average, and now we use a Poisson approximation. What is the probability that number of defective lumps is greater than 15, so that we run out of lumps? Well, we can approximate it with Poisson distribution, and when we sum up all these Poisson probabilities with parameter 9, then we get the result approximately 0.02 approximately. Okay. Now, let's see how good this approximation works. Let's compare it with exact binomial distribution. What is the exact probability? We do exactly the same summation, but instead of Poisson approximation, we now substitute the actual formula, actual binomial formula. And the result that we obtain is also 0.02. It's not exactly the same. There is a difference in the third decimal, but for practical reasons, you would say, okay, the probability is slightly more than 2% that you'll run out of bulbs on particular day. So you can expect that in 100 working days, couple of times it's supposed to happen. So this is how Poisson approximation is used to approximate binomial distribution. This is how it arises, and this is why this Poisson distribution becomes a law of rare events. And if you think of other applications, for example, stars in the galaxy, and every small piece of galaxy, there is a very small probability to have a star, but we have a large space. And therefore, many such pieces, many such say small places in the galaxy, and therefore the number of stars is Poisson distributed. So you can always argue like this: Poisson distribution as a distribution for a number of rare events or rare objects. That finishes this micro lecture, but we will come back to Poisson distribution again in its connection to exponential distribution. But at this moment, I want to thank you for your attention.